Recorded. All right. Hey guys, welcome back to week 7 of Techquitable Futures. This week we'll be going over the topic recursion.
Cool. Awesome. Let's talk some recursion. So this is going to be our agenda. Probably looks similar to previous weeks in terms of structure, but start with our intro, give some backgrounds, and then define what is recursion, give some basic examples, and then we're going to spend a solid chunk of time just walking through more in-depth like interview question type examples, because I think this is really one where it's helpful to see a lot. And then we'll have some questions at the end. We kind of did this, but like I said, my name is Menaka. I'm an FD at Palantir. I know that there were some questions about when does the recruiting cycle start, all of that. I think if you ever want to reach out about referrals or if there's a specific company you want to work for, I feel like I both have undergone the tech recruiting process recently enough. And also I feel like I am constantly providing other people information about referrals and companies and hirings and resumes and things. So feel free to reach out about that. Marcus contributed to a lot of these really wonderful slides. He couldn't actually make it for the presentation, but he's also behind the scenes. And Gabriel, I guess you already kind of introduced yourself, but if you have anything to add.
I'm a software engineer at Google. Be happy to discuss anything related to Google if people have any questions. And like Menaka, I'm looking forward to getting to know you.
Awesome. And Gabriel wins the virtual background game, but we should.
I just selected one. They don't have too many that are available.
Awesome. All right. Moving on to the real fun topic of the day. So what is recursion? Is there a hand raising function on Zoom? Can you raise your hand if you've heard of recursion before or studied in your classes? Just trying to get a sense of whether it's well taught. Okay, well, I also can't really see the raised hands, but I'll just move on. A recursive function is a function that calls itself. So what does that mean? Definitely easier to see via an example. So we'll throw it back to whatever, maybe high school or early college math class you may have talked about factorials in. So a factorial of a number is basically multiplying all the numbers between 1 and that number. So factorial of 4, 1 times 2 times 3 times 4, you get the point. So if you look at this third bullet here, you'll see that factorial 5 we can also write as factorial of 4 times 5. And you can kind of see there's this nice visual alignment that allows you to see that you can substitute this 1 times 2 times 3 times 4 with factorial of 4. And so we can abstract that one step further and say factorial of n equals factorial of n minus 1 times factorial of n. And then, if you expand this factorial of n minus 1, that'll be factorial of n minus 1, etc. So that's the very basic overview of recursion. Obviously, we're going to dive a lot deeper very soon. But are there any questions so far? And I should have made it clear at the beginning, recursion can be a pretty difficult concept to wrap your head around. So feel free to unmute at any time or post in the chat. Totally non-judgmental space that we have here. And I guess Kern and Wental and Gabriel relying on you to let me know if there's anything. Cool, we'll move on for now, but lots of opportunities for questions later as well. So I told you this is the recursive function. I was kind of lying. There's something that's not quite right here. Can anyone see what we might be missing?
I think Eduardo's got it. He said it isn't quite right because you need to take into account the base case.
Awesome. That is 100% right, Eduardo. You may have seen my slides before, or you just are a natural, probably the second. So this will recurse infinitely. There's no base case, meaning we'll just keep calling this factorial function over and over again on n minus 1, and it will go on forever. So we definitely don't want that. So let's talk a little bit about base cases, which will be important for every recursive problem that we go through in this lesson and beyond. So in this case, for factorial, when n equals 0 or 1, that is our base case, and we actually want to return a number. We want to return 1. That's because I said, right, the definition of the problem is that you are multiplying all numbers between 1, which is the first one, and whatever n you're trying to get to. So if you have factorial of 4, you know, that's 4 times factorial of 3, which is 3 times factorial of 2, which is 2 times factorial of 1. But factorial of 1 or factorial of 0 should both just be 1. That's the end of it. So it's important to think about your base cases, like I said before, or else your function is just going to keep calling itself infinitely, and that is not going to make you or your, I guess, function happy. So let's keep going and think about how we might actually implement this in code. So we kind of talked through the algorithm of factorial. Let's take a second, and if you want to post in the Zoom chat a pseudo-coded or any sort of like code implementation of what we just talked about. I know Zoom chat is not the best for posting code, but feel free to just use colons or semicolons or whatever it may be. I'll give you guys a few seconds to try that. I'll assume you're all frantically typing. Anybody? All right, we got one from Eduardo. I see. If n equals 1, return 1, else n times factorial of n minus 1. Okay, awesome. And I realized maybe after we show this one, it'll make more sense of what we're expecting in the Zoom chat. But yeah, that is great. So if n, here we have is if n is 0 or 1, because that's how we defined our base case, return 1, else return factorial of n minus 1 times n. Any questions about this implementation that we have here? Okay, let's keep going. But you know, these slides obviously are will be posted later, and so I think it's really helpful to just go through and think about, if I actually have factorial 5, what would that look like? Factorial, that would, you know, call factorial 4, which would call factorial 3, which would hit the base case. So keep that in mind as we're kind of going through more and more complex examples. Oh, just kidding, sorry. We have one more thing we need to do on this solution, which is think about the time complexity and the space complexity. So I know you guys have talked about time and space complexity in a sort of arrays or string problems, which can be sort of sometimes easy to reason about when you have something like a for loop that you're going towards. Recursion can be a little trickier, but I'll let you guys take a stab of what you think the space and time complexity of this might be. Just throw out a guess. Any guess is totally fine. I see the chat. All right, we got an O of N. We got an O of N from Maria, from Eduardo. Lots of O of N's. This is your time to jump on the bandwagon if anyone else wants to post an O of N and be a part of the crowd, or if anyone wants to disagree. Okay, we got 3 O of N's, and the O of N's take the cake. So in this case, it actually is O of N for the recursive solution, because you're basically, if you think about it, you are calling, you're making only one recursive call for each time that you call one extra, like when you're going down the stack, you're only making one extra call each time you call this function. And I think another way of thinking about it is, suppose you expanded, and I realize I should probably figure out how to, yeah, whoops. Sorry, clearly I am incompetent, don't know how to use Zoom. Cool, I won't try to annotate because that didn't work well last time. But for where it says factorial of n minus 1 times n, a way to think about time complexity, right, is like how many computations are you making? So when you call factorial of 5, for example, you have 5 times factorial of 4. So that's one computation. Then you have factorial of 4, which is 4 times factorial of 3. So that's 2 computations. Factorial of 3 will add 1 more. Factorial of 2 will add 1 more. factorial of 1 will add 1 more. So you'll end up having approximately 5 of those multiplications, even if you kind of expand everything, like, you know, Russian stacking dolls or whatever visual is going to work best for you. And so that's why you are all correct in that the big O time here does end up being O of n, and the space on the stack, because it's the number of functions that you're calling, you only end up calling n, or like 5 in our example of those. Cool. For our next example, we'll talk about the Fibonacci sequence. So another sort of throwback of one of those math concepts that you learned at some point in your life and may not have thought about since then until now. So this is the Fibonacci sequence. Perhaps at some point, Gabriel, with his extensive math background, will tell us all of the cool things in nature or otherwise that can be represented by the Fibonacci sequence. But for now, we'll stick to sort of just the boring algorithmic implementation. So in plain English, you can find a Fibonacci number by adding together the 2 previous ones. So here we'll see 2 is the sum of 1 and 1, 3 is the sum of 1 and 2. So how we're representing that here is Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. Of course, like I said before, we're going to be very sad if we don't have our base cases. In this case, our base cases are 0 and 1. So if it's 0, return 0. If it's 1, return 1. So we'll try this again. I know last time we had, again, was it? Yeah, Eduardo posted. Let's see if we can kind of get 3 or 4 more people to post some ideas of what a pseudocode implementation of this might look like. And then we can do, oh no, I'm the worst. Okay, hopefully you guys didn't see that, but we can do the big reveal. Oh, and I saw, is it Horatio? I just saw your question about O of n space because of the call stack. That's exactly right. So it's the number of calls that we're making will end up being n calls because we have like, what do we call it? Factorial of 5, factorial of 4, factorial of 3, factorial of 2, factorial of 1, and then we return. So you end up, and you know, only end up storing like 1, you just need to return that value for each call that you're making, so it ends up being O of n. Okay, well, you guys all should be posting since I already gave you the answer. So I'll give you a second to, if for those of you who are very fast readers, to take a stab at this implementation again. I feel like that scene from Ferris Bueller, where he's like, Bueller. I don't know, Kern and Wenta, if you've made that reference before when presenters are sitting in silence, waiting for things.
I feel like this is where we should be playing the Jeopardy music, right?
Yeah, the Jeopardy music. Oh no, okay, answers are streaming in. They're streaming in. All right, anybody else? We got some good ones here. Okay, I am satisfied with the 2 answers we've got. Let's reveal solution here. So yeah, I think actually both of these are yeah, a little different from the way I implemented it, but definitely yeah, definitely there. So we have this Fibonacci of n. You can do this in a few ways, right? So if n is in 0 or 1, return n is the way that we did it here. So it's just kind of a cute, like, fancy way of just saying if it's 0, return 0. If it's 1, return 1. And then your actual recursive step here is else you return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Cool. Any questions about the implementation here? I know sometimes it can get a little bit more confusing when we add the multiple recursive calls. Same time and space complexity is the problem. Wow, you are very much reading my mind of what I'm going to ask you next, which is what is the big O time? So it looks like Horatio's guess is that it's still big O van. Any other guesses for what it might be? And hopefully I saved that so that no one actually saw it. What do we have in the chat? All right, getting on the O of N wagon again. Okay, a lot of people guessing O of N. Does anyone want to take a stab either by unmuting or in the chat of why they're thinking O of N? Like I said before, a good way to think about time complexity, right, is what are the number of computations that are going to end up being made, or like how are the I'm going to call this same function recursively, but how will it kind of sprawl out, and how many times will we actually end up calling this function that's making this one like addition computation? Cool. A lot of people guessing O of N. Anyone else? Any other non-O of N guesses? Okay, for the sake of time, I'll keep going. So in this case, it's, oh, actually, I just see there's something else in the chat. Okay, another O of N. Cool. So like I said before, yeah, it can be a bit confusing sometimes to think about recursive runtime complexity, which is why I wanted to delve into this specific example, because this one is actually not O of N. So let's talk about why. It's actually 2 to the N. So we'll think about one specific example. So if I call f of 5, and I'm just saying f is Fibonacci, it's going to split into f Fibonacci of 4 plus Fibonacci of 3, right? But then what is it going to take to actually come up with Fibonacci of 4 and to actually come up with Fibonacci of 3? That's also going to split into 2 recursive calls of Fibonacci of 3 plus Fibonacci of 2 to get Fibonacci of 4. Same with Fibonacci of 3. So unlike the previous factorial example, which is one like call of the recursive function only ever led to one call of the recursive function, in this case, because we're calling the Fibonacci method twice in one, or like we're calling it twice in the recursive part of our call, we'll actually split, and each state will generate 2 other states of that function. And so the number of computations we're doing, as if you can imagine, like the same visual I had before of what would happen if you actually inserted this addition and like split it up over time, is that it's actually going to end up being 2 to the N, since you're having to branch and make 2 recursive calls for every time you call Fibonacci. Cool, that's definitely a lot to wrap your head around. So any clarifications or questions there? Or I don't know if, Kern, Wentao, or Gabriel, if you have anything to add there, that might add a little bit more clarity. But the point I'm basically trying to get across here is that though the solution can oftentimes look pretty elegant and nice when you come up with a recursive solution, you actually want to think about like how much are you adding to your time complexity and space complexity when you're branching out and calling the same function multiple times.
Is the space complexity also 2N?
Yeah, so basically you are making like the same, like you can imagine it as like, what are the number of time, well actually, let me think about this. Now that I think about space complexity, I'm actually not sure, like, yes, I think my immediate solution to that would be yes, because you're making like the same branching of function calls. But actually, Gabriel, do you have a sense of like, I'm not sure if there's like any caching that happens. And so if you've already called Fibonacci of 3, you may not have to call it again.
Well, there's no caching in this solution. It's possible to add caching, but that adds complexity.
Yeah, so the point that I would emphasize there is that like in this case for the Fibonacci implementation, you actually using recursion is not your best move. And I will, in a second after I transfer to Gabriel, like post a link in the chat that you guys can look at later, which is like, what is a better solution for Fibonacci? It depends if you leverage an array, right, says Karin. Yeah, like Gabriel mentioned, I think there are ways in which you can keep track of the computations that you've already made. But in this case, each of these Fs is like one function, so to speak, that you're adding to your stack. And so you're basically going to perform to do the n of those. That's a really good question. Thank you. All right, let's keep on rolling. I'm gonna transfer ownership now of the screen share to Gabriel, who's gonna take us through some sample interview questions. But yeah, thank you all for all the great participation so far. And I'm sure that this will continue to be helpful as we go through more problems.
Okay, just a sec. Let me make sure I do it the right way.
No worries, no worries.
I never use Zoom, so
yeah, honestly, I feel like all of you students are so much better at using Zoom because I guess you've used it for classes and things, right, for the last year or so. But I am very Zoom illiterate.
Let's see. Okay, I guess
Zoom is superior. Yeah, they have us using like WebEx in my company. It's not ideal.
Can people see this now?
Yep, I think it's okay. Yeah, perfect.
Okay, great. Okay, yeah, thanks, Medika, for that great introduction. You might be asking yourselves, why bother? Why bother with recursion if we have all these issues with runtime complexity? Even with calculating factorial, we have this thing with space complexity that we don't have with just an iterative solution. And now it turns out that we can modify our recursive solutions to handle that. In the case of factorial, you can kind of add an accumulator, but then that makes it a little bit more complicated, and you still may not be sold on why we would ever want to bother. So I want to go over some examples. These were created by Marcus, but I think they do a really good job of explaining why recursion can be natural. And the first example, oops, oh, sorry, I have to go. The first example involves a symmetric tree. So I guess the first order of business is to just remind people of what a tree is. We're talking in this case about binary trees. Essentially, a tree is made out of nodes, which will have left and right children, which are themselves trees. So it's itself a recursive data structure. And you could also say a tree could be empty. So you could have nothing, that's a tree. You could have one node. You could have a node with like nothing on the left and something on the right. And it ends up with something like what we see on this page here. So given that it's a recursive data structure, a kind of natural way of dealing with it would be to say, in general, if we want to process a tree, we somehow want to have an algorithm that acts on trees. It does one thing on the node, it does one thing on the left subtree, basically calls itself on the left subtree and calls itself on the right subtree. And again, as we've seen before, we need this recursive step, but we also need a base case. Okay, so that's the preamble to this. The problem that I'm going to be trying to solve is, given a binary tree, check whether it is symmetric or whether it's a mirror of itself. So basically that means if you flip it along this dotted line, it should look like itself. In this case, it does. You can see, we've got a 2 in the middle, we've got a 2 on the left, a 2 on the right. On the bottom, we've got a 3 on the far right, and a 3 on the far left and on the far right, and 4 on the insides. So when you flip it, you get exactly that same thing. Okay, so here are some examples. So the one on the left is the one we just saw. Yes, this is a symmetric tree. So Okay, why? Let's see. So how do can I see chat from here? I don't know how to see the chat. Does anybody have any suggestions as to why the one in the middle is not?
I can see this chat, so I can act as translator if you
Oh.
need me.
Okay, thanks. Oh, actually, okay, I just need to use different screens, I guess. I can see it now. Right, because 3 and 5 are not equal, exactly. So if you flip them, you would have a 5 on the far left, a 3 on the far right. So it's not the same. Similarly, for the one on the right, if you flip them, the top and middle rows are the same, but on the bottom you have 4, 3, 4, 3. So so it is not symmetric. Okay, so now I mentioned before that in general, if you want to operate on trees, you have a function that will do something to the root and then do something to the left and right children. Now, if we break this down a little bit, this is a little bit tricky. I'm actually going to rephrase the question. Essentially, what we want to do, if you think about it, is assuming the root has children on both sides that are non-empty, we'll have a left-hand tree and a right-hand tree. And what we want to ask is not, are these things, is there some symmetry, but are they mirror images? I mean, I guess that's a kind of symmetry. So you're not asking, is a tree symmetric? You're asking, given two trees, if you flip them, do you get the same thing? And if you kind of go down that rabbit hole a little bit, you would want to ask various questions that we'll try to figure out over the next couple of minutes. What does it mean for two trees to be mirror images of each other? So like in this case, you can kind of see, okay, that you have the twos are the same, that's good. And so if you look at this right-hand image, there are triangles around them. I think that's to indicate that while in this case we have numbers, they in general could be trees. So we basically, the 3 is equal to the 3, which is good. In general, you would want to say the 3 on the left should be a mirror image of the 3 on the right, and the 4 second from the left should be a mirror image of the 4 second from the right. And that's really all you need, plus some base cases. So so really, I think it is possible to write tree algorithms using auxiliary data structures and without using recursion, but it's much more natural and easier to think about if you do it this way. Okay, so so let's just pause and start with the base case. What are the kinds of things that we might want to have as our base cases? I'm open to people chatting about them now.
Because one of them would be if the tree only has one item.
Okay, so there are two trees, so you mean both of them have one item?
Yeah, they both just have one thing in the tree.
Okay, and how would you handle that? Remember, we want to answer the question of whether or not these trees are mirror images of each other.
Yeah, so if they're the same, then we return true. If they're not, false.
Right, exactly, thank you. So if you have a case in which you have one node, then basically they're mirror images of each other if and only if they have the same value. That's great. Anything else?
I guess would a base case be if the left and right child of a tree are null PTR, like to let you know that you've gotten to the end of these trees?
Right. Okay. So if they're both empty, let's say, then what do we conclude?
That you've gotten to the end of the tree, that you don't need to keep recursively.
Right, we have that right.
Mhm.
Exactly. But we have to. I mean, we have to be able to. I'm sorry. So remember that with the base case, we still have to give a result. And in this case, it's a binary, true or false. So are we saying that if they're both null, then it's true?
Yes.
Right. Okay. Right. Exactly. Good. So far what we've seen is that if they're both null, then it's true. It's quite trivial, but it's true that they're mirror images of each other. And if they both have one element, then it's true that they're mirror images of each other if and only if the values are the same. Is that everything?
No, I think one other thing I noticed was like, I think you're comparing of two separate trees, you're comparing like the left and right child and seeing if those children are equal. If they're equal, then that suggests that the tree is a mirror image. So you compare like the left child of one tree to the right of another, and then the right child of one tree to the left of another.
Right. Right. That's definitely something we need to do.
Mhm.
That's not a base case though, right? That's like the recursive step.
True.
I mean, we can get to that, and that's an excellent observation. There's just one more base case we have to deal with.
We have some things in the chat as well. I think Maria's comment for if node is
If
null.
node is null. Okay, right. So remember, we have two nodes. We have two trees, and so which node are we talking about? So far, we have established that if both nodes are null, they're mirror images. And we've come up with a way of handling things if both are not null. What remains? So it's possible that one node is null and one isn't, right? That's the case we haven't dealt with yet. And
Yeah.
in that case, what should we conclude?
False.
False. Exactly. Right. So basically, if both are null, true, one null, one not null, false, both not null with no children, then true if and only if they're the same. And that sounds good for our base case. Okay, so now we touched about this before. For the recursive step, so what we heard was that you have to do a comparison between the left-hand child of the left-hand tree and the right-hand child of the right-hand tree. And what was it that we needed from them?
You need them to be equal.
Well, if they're equal, and if they're equal and then we reflect them, what happens? So like I have a tree, let's say the root is 1, and then it has the left-hand node is 2 and the right-hand node is 3. I have that on both sides. Well, if I take that and I reflect it, what would the reflected version be? It would be, we basically flip sorry, it may be impossible to process it because I'm not writing it down, but the 1, 2, 3 would become a 1, 3, 2. So remember, when we flip things, we want mirror images, right? So we don't want to say like if I flip the left-hand tree in general, I get the right-hand tree. Right? We want to say, sorry. We do want to say that if I flip the left-hand tree, I get the right-hand tree, and that doesn't necessarily mean the left-hand tree is equal to the right-hand tree, right? So for example, if I have a 1, 2, 3 and I flip it, I want to get a 1, 3, 2. So we don't want to say that the left-hand subtree is equal to the right-hand subtree. Right. So what would we say? What would we want to have happen if we flip the left-hand subtree on the left tree?
they should compare the left and the left and the left tree.
Well, we wanted, okay, so we want to compare the left and the right, right? And what I'm saying is that we don't necessarily have to have them be equal. What we want is basically when we flip the left, the flipped version is equal to the right version, right?
Yeah.
So I guess, I mean, if those trees are themselves symmetric, then it's okay for them to be equal. But if they're not symmetric, when we flip them, we'll get something different. So essentially, we want to, when we flip, unfortunately, let's see, just maybe I can go back. So imagine that on the right-hand side, we have a kind of triangle around the 3 on the far left and the 3 on the far right. If you can imagine coming from that 3, let's suppose we have a 5 and the 7 on the right. So we've got instead of a 3 with children, 5, 7. What we want is when we flip it, we need to get 3 with a 7, 5 coming out. So they have to be essentially mirror images of each other. So that's kind of the inductive step. The left tree's left subtree should be a mirror image of the right tree's right the right tree's right subtree. And similarly, same thing with the 4s. When you flip the left tree's right subtree, you need to get the right tree's left subtree. So essentially, the trees that are represented by the 4s have to be mirror images of each other. Okay, so are there questions on that? That may be a little bit hard to process. Okay. Any? Mm-hmm.
I said, yeah, it makes sense.
Okay. Okay, so then let's just keep going. So, okay, so things to think about, base case. Okay, if we reach the end of the tree, we talked about that. Conditions for them to be mirror images. So the root nodes values, if they're not empty, must be the same. And this is what we were just talking about. The left subtree of the left tree and the right subtree of the right tree have to be mirror images, and similarly for the others. So now let's try to write it out. And this is kind of nicely written in such a way that we have some of it written in and some of it isn't. One important thing to note here is that we need a way of going from what we're trying to solve, which is to tell whether two trees are mirror images of each other, to whether a single tree is symmetric. And essentially, to be symmetric is the same sort of thing as being a mirror image of itself, right? So being symmetric means when you flip it, you get itself, which is the same as saying it's a mirror image of itself. So that's kind of the code at the bottom. Now the question is, how do we write this out? Does anybody want to try and write in these base cases in the notes? The base case and the check symmetry and recurse step.
And the try it more cloud comes from last year when another one of our presenters would give you clout every time you post them in the chat. So keep that in mind.
I will give double clout if there's anything in the next 20 seconds. I'm not sure what clout is, but this is a special offer.
All right, David coming in for some clout. Still have a few more seconds for anyone else. Well, just
to kind of give a little more detail, what we want to do is we want to just go over the things that we had mentioned before, that we've already got all the algorithm. We want to make sure that we cover these base cases, like if both are null, if are none in Python code, if both are none, then we return true. If and in this particular case, it looks like the code is actually returning false if we fall through, like if one is none and one is not, then one is not none. In the check symmetry and recurse stuff, essentially we want to do the things we just mentioned before, which means we want to check that the left, so we have this is mirror thing. We want to call is mirror on the left-hand child of root 1 and the right-hand child of root 2, etc. Okay, so let me just go down. Okay, so again, root 1 is none, root 2 is none, then return true, which is one thing we went over. And then here, okay, so right. So if the root values are not the same, then looking at this code, what is going to happen? We just won't do anything, we'll end up returning false. So this code is structured in such a way that if the things we don't want to have happen, if conditions for it not being mirror are not met, we just fall through to the very end. So the question is, if the root values are the same, then we have to return, essentially, as we said, is mirror root 1 left and root 2 right, and is mirror root 1 right and root 2 left, right? Which is just saying that the various subtrees we looked at are mirror images of each other. So, I mean, looking through this code, if we have a tree, we want to call is mirror on the tree in itself. Again, if the tree is empty, essentially we will return true. Otherwise, assuming we have a single tree, we're going to look at the values. Well, I'm actually, if we're looking at a tree, the root vowels are going to be the same. So we're essentially calling is mirror on the left hand subtree and the right hand subtree. And then we go, basically this recursive solution will keep going until we reach nodes that don't have any children. Like that would be like the 3 and the 4 at the bottom. Okay, I think that's it. Yeah. So okay, that was so that's a pretty involved example, and a lot of things to bear in mind. Are there any questions? So I hope, I mean, I think it's a lot to absorb, but one thing to bear in mind, at least, is that it's the kind of problem that's very well suited towards using recursion, because ultimately we're just saying, okay, if you look at the algorithm, all we're doing is we're looking at what happens to the root of the tree, and then we're calling the function itself on subtrees of the tree. And this is like something that generally happens with tree algorithms. If you want to do it without recursion, it's more difficult.
And I think there's a question / a guess at the time and space complexity in the chat.
So if one, sorry, let me go through this. Let's see. So what if a tree is not complete? You could, so complete, I guess, means that you have some nodes that are null. You could have, I mean, imagine that you had a tree. So imagine you had a tree that let's see, I mean, you could have a tree with holes in it that's still symmetric, essentially. So it's not it's not necessarily false. If one of the trees is null, I mean, okay, so if we're doing the mirror image thing, if one of the trees is null and the other isn't null, then it'll be false. And we kind of capture that by just looking at the root node of the non-null tree. Yeah. And I don't think we have any slides on time complexity. So I just assume go on to the next one. It's essentially what you have to do is, yeah, I'd rather just go into the next one if there aren't any questions on that, because we have a lot of stuff to go over. This is only one example out of many, so maybe I'll speed up a bit. Okay, so now I'm going to talk about sanitizing an object. And essentially, it means that we're replacing text in one string with another string. And the data structure we're using here is JSON. So a JSON object is essentially, so this is also a recursive data structure. And it's a dictionary in which the values can be basically three different types. One is that they could be primitive types. We can just say for now, let's say integers or strings, or they can be an array. So an array is just a list, and the elements in that list are themselves objects. So basically a list of objects. Or the value could just be an object itself. So we see examples of that here. The first two have values. Marcus, that's a string. Age 26, that's a number. And then we have an array. In this particular case, the elements of the array are primitive types, but they don't have to be. They could be basically these dictionaries themselves. And for the employer, the value is an object. And so the task is basically, if you want to basically replace every instance of one string with another string. The thought behind it is maybe you have an exposed password and you want to replace it by just some stars, but it really could be any kind of general case where you have one string you want to replace with another string. And so the function that we want to write is called sanitize object. We pass in the object, we pass in the string that we want to replace and the string that we want to replace it by. This is the problem statement. That's a little bit hard to see, but you could see, so in these slides that Marcus created, anytime you see the word corgi, you want to replace it by star, star, star. So if his password is corgi, replace that by the 3 stars. 12 Corgi Street, replace that by the 3 stars, etc. Every single time you see it, you replace it. And I think now just writing a function that replaces some kind of text with another kind of text, that's like a whole interview problem unto itself, but we're not going to make that part of this discussion. So instead we'll assume that we have such a function that we can call. So replace string with A and B, and all we have to do is call that. Okay, so before I go on, are there any questions on the meaning? Oh, 6 new messages. Sorry. Sorry, I don't have time to read through all of this. You can't see the new slides? Oh, can people see these now or what?
Yeah, what I see right now is the slide that says example on the top in red.
Okay.
And the
Okay. Okay.
Okay, awesome.
So,
very good.
Okay, right. So I guess my question is it clear what we want to do? We have this data structure and we have to somehow go through the data structure and do the replacement. And it's not, we're not saying like you take the data structure, you write it out in something like we have here, just write it out in, on paper and then, or on your screen, and then do just a string replace on that. Instead, we're passing in this data structure. So we just have like the user data structure, and we have to basically recursively go through and figure out where all the cases that corgi occurs and replace them. Okay, so simple question is, maybe the simplest question, given a string, a corgi bit me, how do we replace it? And as I said before, we can just assume there's a function that does it. Yeah, so string.replace. I think that it doesn't really matter too much. The point that's being made here is that it should be in place. If it's not in place, then you would just have to reset the value of the key to the replaced value. In other words, in place means you call it, it's a void function, you call it, and target is mutated. From then on, instead of being the string a corgi bit me, it's the string a star 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 bit me. If it doesn't mutate it and it just reproduces a new string, then you just have to replace the value with that new string. But that's not something we need to worry about too much. Okay, so the next observation is, well, if we had only primitive types, what that means essentially is we have a dictionary where some of the values are keys and some of the values are strings and some of the values are integers. So all we have to do is simply go through for each value. If it's an integer, we replace it. We don't do anything to it because an integer doesn't have to be sanitized. And if it is a string, then we call this replacement function. Okay, so now the question I'd like to ask is, does this work in general? If not, what should we do? So remember, the structure of JSON is that the values are not necessarily just these primitive types. They could also be other types. And we also have a function where we're passing in an object and then the password in the sanitized string. So as we're writing this function, what I guess I could ask, what is wrong with what we have so far? Okay, the issue is if it's not a primitive type, it could be, for example, an array, right? Right, okay. Okay, so you'd have to check the array to see if there are any strings. So how would we do that? Just assuming we do have an array. Okay. So what do we do with arrays? We iterate over them, right? And when we iterate over the arrays, we're going to, in general, get okay. So right. Okay. So you go through the array, and if the value is a string, then you can do something similar to that. What if what if the value is not a string? So the value could also be an object, right? And so if it's an object, then we want to make just this recursive call. Okay, so let me just let's see. Okay, go through this. So if it's a string, we do this, right? This is what we've seen so far. Now, if it's an array, then, okay. So basically we're iterating over the array. And then we basically have to call sanitize on each element of the array. Okay, which the elements of the array are objects, right? They could be containing strings, but we just want to call sanitize object, which is the same basic thing on each element in the array. And then if it's an object itself, then, okay, so then basically we have to go through each of the values and sanitize them. So now, this is basically breaking down sanitize object into the three different cases we have to deal with. What about the base case? So, let's see. Going back, essentially the base case, I mean, you could imagine it this way. The base case would be there wouldn't be any objects at all, right? And so you wouldn't even have to call anything on, there wouldn't be any values at all to call it on. You would have an empty dictionary. Okay. Any questions? I think that the next example may be a little bit more, okay. So we got some, yes. Okay, fair enough. So yeah, JSON is itself a very common data formatting language, I guess you can say. It's used widely. It's not used a whole lot at Google, but it's common, and so it's useful to know. So here's an example Marcus provided in which we don't have to go through every detail, but the point is that assuming you have a function that can convert what's sometimes called snake case to camel case, if you have a variable like a underscore b, you would convert it to a with no underscore capital B, and you might want to run that on like all objects in some kind of code. This would be a way of doing that. Okay. So I'm gonna move on, I think, to the last problem is kind of interesting. Are there any questions before I move on? Okay. Okay. So hopefully this next one will be a little bit more interactive. So the problem statement involves having a grid where you want to, basically you've got a bunch of squares and you want to start at the top left and go to the bottom right. And some of them may be blocked off. So the question is, how do you find the number of ways of doing this? So let's just, before we think about things being blocked off, let's look at a simple example. In fact, let's suppose we have just a 2x2 grid. Okay, and so nothing's blocked off, and you can move only right and down. You start at the top left, and you want to end up at the bottom. How many ways would there be of doing that? So basically, at any given square, you only have two options for how to move, two at most. If things are blocked off, 4 ways, 3 ways. Okay, can people tell me what the ways are? Let's suppose we could use an R for going right and a D for going down. So okay, so it's 2 by 2. So we're only going to go down 1 time. So you could go, okay, one example would be going down and right. Right, and just you start at the top left, you go down, and then you go right. And what would be another example? If you go right, so you want to end up at the bottom right. So you could go basically you could go DR or RD. Right? Those are basically go down and one to the right, or right and then down. Does that make sense? Because it's 2 by 2, and I mean maybe it's not clear, but you kind of imagine yourself being like in the middle of the block. So you're going. It's not like you start at the top left-hand corner and then you're going 2 down. You're kind of going from the middle down or from the middle to the right. So you only have to go right once and down once. I'm trying to understand whether this is clear. Can people like let me know whether it makes sense? Okay. Yeah. So, okay. Right. So, right. Not on a corner of. You're not on the corner of it. You're just right in the middle. Okay. So let me go over a couple more examples then. Suppose it has, let's say, only 1 row and we have 5 columns. How many ways are there of going from the top left to the bottom right? In this case, top and bottom is meaningless because there's only 1 row. There's only 1 way, right? We just go right, 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 right. Okay. Okay, so now let me just try one more. Suppose it's 3 by 3. Okay, so 3 by 3. So you have to go down. You have to go down 2 and right 2 in some order. How many ways are there of doing this? So can somebody maybe give an example? Again, we're going to have 4 steps, right, with D's and R's, because we're going down 2 and we're going right 2. Okay, RRDD, that's 1. Right, good. Okay, so how many are there total? Is that it? Mm-hmm. And let's see, did we say RDDR? So there are 6 of them. Right, there are 6 of them total. Now, I won't go into it too much. I'm just going to say for people that care, if we're if we have something, let's suppose it has n plus 1 rows and then m plus 1 columns. There's actually a mathematical formula that tells you exactly how many ways of doing it. In this case, if there are n plus 1 rows, you're going to have n r's and m d's, and so a total of n plus m steps. And you can kind of think that you choose among them which of those n plus 1 are going to be going right. So it's for those of you that are familiar with like n choose m notation, it's n plus m choose n. So the point is it's a huge number, but also it's something that we can calculate analytically. You don't have to worry about that. It's just there's really a large number of ways of doing this, and you don't need to use any kind of recursive algorithm. Okay, so having said that, that's just kind of a preamble. I just wanted to make sure we were clear about the nature of what we're doing. And now we're going to be introducing these impediments. So let's look at the example that's 3 by 3 with a star in the middle. So, so how many ways are there going to be of getting from the top left to the bottom right here? We saw that if there weren't any stars, there would be 6, right? In this case, we've got a star in the middle. So how do we, like, what, if you were to just look at this and somebody says, okay, you have to drive a car from the top left, or walk, I guess, from the top left to the bottom right, what would you do? Only 2 ways, right? And what are those? Exactly. So basically, we just go all the way to the right and all the way down, or we go all the way down and we go all the way right. Okay. And you know, the larger example, that's 4 by 4, that's a little bit more complicated, and you could definitely try to count them all, but what we'd like to do is, well, what kind of solution do people think we're going to try to find? Recursive solution. Okay, so now the question is, how do we create a recursive solution to a problem like this? Right, a lot of question marks, because it's kind of, we don't want to put ourselves in the position of having to count things. Instead, we like to just code up something and then just run that code to figure it out for us. Okay, so now how could we begin to think about solving this recursively? And like any general thoughts as to the approach we could take? So, like, imagine we're starting at the top left. How could we move from the top left?
Just move right or down.
Right, move right or down, assuming there aren't any stars in the way, right? So, so how can we relate the, let's suppose that for now there aren't any stars in the way. How can we relate the total number of solutions to, let's say, well, what can we, how can we leverage the fact that we're one to the right? What could we do with that? And suppose we're trying to think of something recursively. The idea is that we could kind of imagine another problem. We've moved one to the right. We can imagine another problem in which we've just gotten rid of that left-hand column. And now we just want to calculate the number of ways of getting from that one to the right spot. to the bottom right, right? That'll be some number. And we can do the same thing with moving one down. We just get rid of the top row. And we'll have some number of ways of getting from that new position, one basically in the first column and second row, some number of ways of getting from there to the bottom right. And if you think about it, I mean, the number of ways of starting from one to the right is going to be different than the number of ways of going one down, because they're always going to be different paths. So what can we do with these two numbers? Suppose there are, okay, so if we go back to this one, okay, so I moved one to the right, right? Can people see my mouse, my cursor? Okay, good. So once we've moved one to the right, there's only one path in this case, right? We just go all the way to the right and all the way down. Once I've moved down one, there's only one path. Just go down one more and move all the way to the right. And all we do is we add these up together, right? So we could do the same thing with this bigger one. We could say, okay, for this bigger one, I can move one to the right. And now instead of a 4x4 grid, I've got a grid with 4 rows and 3 columns. And I could imagine all the different ways of going to the bottom. And similarly, if I've moved one to the right, one down, then we can imagine a situation in which we have 3 rows and 4 columns, and I can count the total number of ways of going from this spot in the second row and first column to the bottom, and I calculate those and I add them up. And that's basically our recursive step. Let's see. So I think basically maybe the point is that we can move either to X and go all the way down, or we can move to Y and go all the way down. We add these together. Okay, so that what I've just been going over is essentially this middle point. Paths from a given point x, y is equal to the number of paths from x plus 1y plus the number of paths from x to y plus 1. And of course, we could say maybe, if we've moved to a star, then there are no paths. Okay, so any questions? Makes sense. Okay, good. So the fundamental observation here is that there are only 2 ways, at most 2 ways to go, and so we just take the number of ways of doing it starting from 1 to the right, and add that to the number of ways of doing that starting 1 down, and bearing in mind that if there's a star, we're blocked. So, okay. So now, what are the base cases? What if we had only one square? What would the number of ways of doing it be? This is kind of like a super trivial case that, I mean, there's nothing to do. So like, all you could do is just stay there, and that we would count as being a way. So there's one way. Okay, and what are some other things we have to bear in mind? So I guess the way to think about it is that we're always either moving right or left. Always moving either right or down. And so we may just move to a star. So we could say if we've moved to a star, then nothing, or if we've moved off the grid, then nothing, we're done. There are other ways of doing it, which would be maybe to say, like, if there's a star to the right, then don't even think about moving there. But we can, we could do it this way. This way will make things work. So let's see. Does anybody want to try to express basically what we would do here? It may be a little bit complicated. Maybe just like in words. Okay, I think probably people are pretty tired. It's been an hour and a half of recursion, which is a lot. So maybe I'll just kind of explain it. And actually, there are two solutions, and I think maybe I'll skip the second solution. Basically, what we want to say is that, oh, okay, so before going into too much detail, a bit about length. Basically, you could kind of view this as the grid. We could represent the grid as an array of arrays. So grid.length is the maximum number of rows, and we're assuming it's a square. So grid 0 of length is going to be the maximum number of columns, and I mean it should be the same as grid 1 of length, grid 2 of length, etc. So if you look at this very first if statement, what it's basically saying is that if we're off the grid, or if the entry in the appropriate grid item is not empty, then return 0. So basically, we were talking about stars. Saying that it's not equal to the empty string is equivalent to saying it's a star. We can assume that either we have an empty string or we have a star. So as for why we're looking at row versus grid.length, so suppose we have 4 rows. So then grid.length will be 4. And so the valid rows would be 0, 1, 2, 3 because of 0 offsetting and such. So if we actually got to a 4, we've gone too far. So you can kind of imagine we're starting at row 0. We have 4 rows. We go down 3 of them. Then the algorithm tells us to go down 1 more, and then from that point we're just going to return a 0. Okay. So this is basically dealing with places where we can't move at all. And the other base case that we need is the one in which we're basically at the bottom. If we're at the bottom, there are no other ways of moving. I mean, if we didn't have this last step and we got to the very bottom, we'd never know we were done, right? It's kind of similar to the case where we have exactly 1 grid element. So the grid.length is 1 and grid of 0.length is 1. In that case, we saw that we return 1. So that's a way for us to end. The other ways are kind of a way for us to prune our movements. This is one for us to know we're at the end. And then what this tells us is we simply do what we were saying before. We add the number of solutions from moving 1 down plus the number of solutions from moving 1 to the right. And if we, again, if we move off the grid, then we'll get a 0. If we're at the end, we'll return a 1. Otherwise, we'll just continue with this, with these recursive calls. And you could look at this other recursive solution. It's basically the same thing. It's doing it in such a way as we're not going to be worrying about going off the grid, so to speak. And you're welcome to look at the notes afterwards. Okay, so so in terms of big O, let's just say we went over before about the fact that if you have an empty grid, there are a bunch of different ways of calculating a bunch of different ways of going from the top left to the bottom right. And this is what I mentioned before. Yeah, these kind of problems also show up sometimes in interviews, but it's not exactly what we're focusing on here. So I wouldn't invest a huge amount of time in this unless you're unless you're really interested in it. The key point here is that there are many, many different ways. And the reason that matters is that if you think about it, for our algorithm, we're not memorizing anything, right? We talked a little bit before about how we don't cache things. And in this case, like going back, let's see here, we're just starting from scratch. We move down one, we start from scratch, and we're going to be repeating a lot of calculation, a lot of computation. So it's really, really slow. So the question is, yeah, can we do better? I'm just going to like talk about this just very briefly. The key point in addressing shortcomings of recursive algorithms is that oftentimes we may want to find a way to cache information so we don't have to calculate it over and over again. And with this kind of problem, what you can do is for every point in the grid, you calculate the number of ways of getting there from the top left. So not only are we going to calculate the number of ways of getting to the bottom right, but take any random point in the grid, we're going to calculate the number of ways of getting there starting from the top left. And then that's useful because at any given point in time, if you have a random point on the grid, if you know the number of ways it takes to get to the one to the left, and you know the number of ways it takes to get to the one above, then you just add them together. And that's like an introduction to dynamic programming, which I guess we're not going to cover this in this course, but you could read about if you want. It makes things go much faster, although they're hard problems. So thanks for listening to all this. Is there anything else here? Some questions. Yes. So some topics that you can read about, some problems.
Yeah. Cool. And then I also I know like you guys asked some really good questions about big O notation, and I said I also would promise a link. And so I would recommend reading through this. What I previously said about the Fibonacci being 2 to the nth space, I remember who asked that. Actually, I was mistaken. And as you know, they posted in the chat earlier, what you actually want to think about is like, what is the maximum size your call stack would be? So for any of these problems, a good question to ask is like, how many times am I going to call this function for trees? Like how many nodes am I going to visit? And what am I going to do on each time I call that function? So if it's constant and you have n calls, then you'll be O of n. But if you have, for example, 2 to the n calls like we did for Fibonacci, that's when you have to sort of reconsider. So yeah, hopefully that link is a little bit more helpful. But thank you all so much. Loved the amount of participation here. I don't know, Lentao, if you have anything else to close it out.
Yeah, I mean, thank you guys so much, Monica and Gabriel, for kind of going over this like difficult topic. You guys really did it in a fantastic way, and that made it easier for everyone to understand. So thank you guys, and also thanks for the fellows, who have kind of continued to stay engaged with this difficult topic. I know this is a little hard and long, so I'm going to just give a little summary. But first, Monica started out with the definitions and examples using factorials and Fibonacci numbers. And you guys can see how important it is to come up with the base cases and try to understand what is a recurrent structure that you can kind of call the recursive function on. And then later we had Gabriel kind of go over the 3 examples with symmetric tree, sanitizing password in a JSON object, and lastly to kind of calculate the number of paths to get from the starting point to the endpoint in this grid, right? And then you guys saw how, once again, the base cases comes up again. It's really important to identify what they are, and also see, okay, what is a recurrent structure in which you can call the recursive function on with a slightly different parameters to input. So then they will kind of calculate those like recurrent structure for you. And lastly, yeah, as Gabriel mentioned, like this is also like a really nice segue into dynamic programming. With recursive function, there may be some input or cases in which you're calculating over and over again if you're not caching them. So if you do cache them with like some helper data structures such as like hash or like your table, that's the way in which you can like really optimize your computation time and and just cut down your runtime. So that's how you can kind of get to the dynamic programming solution. So yeah, just a little summary to kind of like wrap everything together of like everything that we went over today. But thank you guys so much. And yeah, feel free to kind of post any questions on Slack if you guys have any. Otherwise, I'll follow up with the recorded lesson, the slides, info mentors for this week's mentors guide. So thank you guys so much, and see you guys around.
Have a good day. See you next
Thank
week.
you. Bye.